The next video on frequency response looks at plotting and using Nyquist diagrams. So far then, we've summarised frequency response by these two simple formula, the gain of G of S and the phase of G of S. And we've shown how this data can be plotted in a Bode diagram with separate plots for gain and phase. Now what we want to do is explore what happens if instead you plot this data in an Argand diagram of the complex function g of j omega. And we want to know, why is this plot useful and how is it utilised in feedback design? Here's an example then. So you'll see I've taken a g of s, there it is, 1 over 1 plus s, and I've calculated here all the values of g of j omega at certain values of omega, and all I'm going to do is plot them in the graph. So we've got a point here, roughly 0.99 minus 0.1j, and then we've got 0.8 minus 0.4j, so that's going to be about there, and 0.5 minus 0.5j, that's going to be about there, 0.2 minus 0.4j, that's going to be about there, and 0.01 minus 0.1j, so that's going to be about there. And what you can see is if you had a few more values, the plot's going to do something like this, and this arrow is omega increasing. You see omega going from 0.1 to 10 in terms of the table. Now I could do this a different way. I could start from the gain and phase. Now this is a slightly different example, but you can see a gain of 1.98 and a phase of -9. That gives me a point about here. A gain of 1.65 and a phase of -39. I'm not going to be over precise, somewhere like this. A gain of 1 and a phase of -63. And again, you'll see I'm not being overly careful here because I'm just trying to illustrate the point. And you can see if I had gain and phase information, I can plug that in. If it's not clear, by the way, there's the phase theta there. So I can plug that in and I can come up with a sketch by basically putting in all the individual values and seeing where I end up. However, this is really rather inefficient, apart from having to create the table in the first place and then put all the individual values into a graph. It's going to take too long. It's really not worth the effort. So what might you do? Of course, as ever, if you want an accurate plot, you can always use something like MATLAB, and you just use a command, something like Nyquist, and it produces this plot for you pretty much immediately. You'll notice it gives you both negative frequencies and positive frequencies, which is slightly different from the Bode diagram. But the focus of this particular video, we want to look at sketching. We want to ask ourselves, can we get this plot quickly on the back of an envelope so we don't have to turn on a computer? So what guidance do we need for quick sketches? We need to ask ourselves things like, what is happening with the gain and the phase? In other words, is the gain increasing or decreasing? Is the phase increasing or decreasing? And we can put a very simple example here to show you what we're talking about. If this was an Argand diagram and this was a point here, if the gain was increasing, your plot would be going away from the origin. If the gain was decreasing, so you should be going towards the origin. If the phase is increasing, so I need red for that. If the phase is increasing, you'll be going this way, anti-clockwise. And if the phase is decreasing, you're going clockwise. So you can see it's very easy to estimate roughly how is this diagram moving just by asking yourselves what's happening to the gain and what's happening to the phase. And we'll illustrate this in the next few examples. So here we have an example, g equals 1 over s plus 1, s plus 4. First thing I'm going to do is show you why this is a sketch. It's the back of an envelope. So I'm going to do the Bode diagram very, very quickly. Put my corner frequencies, 1 and 4. And if I was to do the Bode asymptotes, I'd just do that. You can see how quick that was. I can see it's flat for low frequencies, then I get a slope, and then I get a steeper slope. What about the phase? Well, the phase goes from 0 to -180. Oops, what's happened there? Something pressed that I didn't expect. So it goes 0 to -180. Now I could, if you wanted me to, I could put in the sort of Bode asymptote type lines like that, and you can see what's going on. So the key thing is, you do your Bode in 10 seconds. That tells you roughly what's going on. So now we move across and ask ourselves, okay, so I've put that line in the wrong place. I do apologise. We want that line more over here. So where do we start? Well, we start at a value of 1/4. Okay, so there's 1/4. That's our starting value for frequencies of 0. And then what happens? Well, you can see the gain is reducing. And what's happening to the phase? The phase is reducing. So in other words, because the gain's reducing, I'm always getting closer and closer to the origin. So I'm moving towards the origin. What about the phase? The phase is going 0 to minus 180. So I'm moving in a clockwise direction. So what you'll see is I must be doing something like this. So you see with that line, what's happening to the gain? If I calculate the gain, which is the distance from the origin, you'll see I've drawn that line so it's always going closer to the origin, and I'm always moving in a clockwise direction. And you can get that sketch very, very quickly from that crude Bode diagram. And you notice, as I finish, I'm approaching the minus 180 degree line. And there's the exact plot, and you can see it's pretty much the same. So a summary procedure, okay? Use asymptotic methods to give a rough Bode plot, a very rough one. Do it very, very quickly. And what you're interested in is what happens as omega goes to 0, what happens as omega goes to infinity, and roughly look at the trends. Is the gain increasing or decreasing? Is the phase increasing or decreasing in between? Now, if you want to do something a bit more with this plot, you do need to be reasonably accurate near -1, and we said the same thing with Bode diagrams. So you might want to think about, how do I make sure I'm reasonably accurate in that region? Once you've got these trends, just transcribe the information into the Argand diagram. But you can see in this video how I'm doing that very, very quickly. I just want a sketch, I just want an impression. I'm not too bothered about it being precise. So here's an example. I've got 3 over s plus 1 s plus 2, sorry. So first thing I do, I think that's the one we just did. You can see we did the example and we just do this. We do, there's our trends, and then we get our plot and we say, okay, I'm starting from 3 over 2. I can see the gain's increasing and the phase goes down to minus 180. Now you see how quickly I did that. Okay, I did a very, very rough sketch of the Bode using asymptote information just to see the trends, what's happening to the gain, what's happening to the phase, and I then just translated that information directly onto the Argand diagram. And the most important thing is I've calibrated it here with the start point. Right, here's another example. Okay, so 3 over s plus 2. Now this one is slightly different because it's got an integrator. So because it's got an integrator, it means the gain is infinite at low frequencies. So I'm going to have to calibrate it with a different point. So what I've done here is I've looked at the first corner frequency and I've said the asymptote gain at that corner frequency is about 0.75. And you remember there's a 3 dB drop off there, so the actual system is going to be slightly below that. So now I need to ask myself, what can I do? Well, at that particular point, the one I've noted here, you can see the phase is about minus 135. So let's mark that in. Minus 135. And the gain is going to be about a half. Okay? I'm not being too precise because remember what I've said. This is a sketch. And so what I now look at is say, right, my plot needs to go through that point. And it needs to start from minus 90, finish at minus 180, and the gain goes from infinity down to 0. So you'll see my sketch is just going to do something like that. Okay, you can see the phase starts at minus 90, and gradually you see the way that plot is moving towards minus 180 degrees, and the gain is getting smaller and smaller. And there's the true plot, if you want to see it, and you'll see it's got the right pattern. Here's another example with an integrator, and you see, again, what have I done? So I've marked a key point here, so I can initialize, and you see at that point there, the phase is approximately minus 180. Okay, And what's the gain? Okay, the gain is fairly close to 0 decibels, fairly close to 1. Now, I'm not being overly precise, but basically I'm marking a point here, okay, with that omega equals 1. Now, I need to be moderately precise. And then after that, what am I asking? Well, the phase goes from minus 90 to minus 270. The gain, always decreasing, goes from infinity to 0. So you see I've got my plot. I can make it more accentuated if you want, but it goes down like that, and then basically it finishes. I've accentuated that just to demonstrate the point. You'd have to zoom to see it on the real plot. So you can see here it approaches the origin in the minus 270 degrees direction, and this one here, it goes to minus 90 degrees asymptotically. So what next? Lead and lag compensation. So we've shown how you can sketch Nyquist very, very quickly, and you might be thinking, yeah, okay, I can do these sketches. What's the point? So let's have a look at this example here, and what we're going to try and do is point out the real significance, and we're going to look at the phase characteristic. So I've got a system G, there it is, and I'm going to look at how does the Nyquist diagram change if I have a lag compensator or a lead compensator. And I've started by doing the bode. The key thing you need to look at is if I look at quadrants in the complex plane, so quadrant 1, quadrant 2, quadrant 3 and quadrant 4. So now look at the bode phase plot and look at the quadrants. You'll see this red plot is in quadrant 2 and the blue and the yellow plots are in quadrant 3. So there's a big difference between the lag and the lead. And again, if you look at the Nyquist diagram over here, you'll see that the lag is in quadrant 2 and these other two are in quadrant 3. Now you need to look at these arrows, they're quite important because the arrows tell you about positive frequencies. So those are the bits that you're looking at. So there's a big difference now in terms of this sketching. So we need to recognize what quadrant are we in when we do the sketch, and this is information that we're going to be exploiting. Before we go on then, we need to introduce this thing called the D contour. Now, CISO tool for the demonstration. Look what happens to the Nyquist diagram as the gain is changed, and then you'll see why this quadrant information is so important. So if I go here and find, oops, gone the wrong way there, I do apologize. Right, so you'll see here at the moment the Nyquist diagram is down here and it's in quadrant 3. So remember the arrows are important. So the arrows going from large gain to 0 are the parts of the Nyquist diagram that correspond to the bode diagram. And you'll see here we're largely down here in quadrant 3. Now, if I make the gain a bit smaller, 0.1, okay, a key thing that you'll notice is this red cross, this -1 point, and we need to be thinking about this -1 point. It's really critical. Let's have a look where the closed loop poles are with these pink dots. You can see the closed loop poles are in the left half plane. There they are. We're a long way from -1, and we can see the plot is down here in quadrant 3. Now what happens as I increase gain? So as I increase gain, watch the closed loop poles. Can you see the closed loop poles are now beginning to move towards the right half plane? The Nyquist diagram is beginning to move towards -1. Increase the gain a bit more, and you see we're now getting very close to -1, and these closed loop poles are getting very close to the right half plane. Let's go to something like 1.5. Bit closer, let's try 2. That might be a bit more obvious. Now, once we get to 2, you can see now the closed loop poles are on the imaginary axis, and the Nyquist diagram is going through the -1 point, and we've got oscillatory modes. And if we go above 2, then you see the poles have moved into the right half plane. We've now got instability, and if you were to blow up on this plot, you'd see that we've gone to the other side of the -1 point, and that's the key thing that we want to be exploiting, and we'll show that it's probably easier to do if we go back to the PowerPoint. Okay, so here's the key point. There seems to be a strong connection between the Nyquist diagram and closed loop stability. If we're far away from the -1 point, we've got good behaviour. As we get nearer, we get oscillations, and if the Nyquist plot goes on the wrong side, we get instability. And this is unsurprising because we know closed loop poles are defined by G equals -1. So if the Nyquist goes through -1, J of omega is a closed loop pole. And if Nyquist plus is close to -1, there must be a closed loop pole close to the imaginary axis, which is not generally a good thing. So the D-contour. How does the D-contour help us? Well, let's just get to the D-contour. What it is something that looks a bit like a capital D. Now, I'm going to do it very simplistically here. You'll find the textbooks will be a little bit more pedantic. I'm just going to draw a big capital D, and the key thing is to recognise it encloses the right half plane. That's the key thing about the D-contour. It encloses the right half plane. You see we've got positive frequencies here and negative frequencies down there, and what those vertical lines are, they're the imaginary axis. Okay, so the D-contour encloses the right half plane, and the key thing is, as you're walking, if you were walking, I'm not much of an artist, but if you were walking up along this contour, going from low frequencies to high frequencies, which way would you have to look to see the right half plane? And you can see you need to look to the right. So if I look this way, I see the right half plane. If I look this way, I see the left half plane. So you need to look left to see left half plane poles, right to see right half plane poles. Now, why is that significant? If you need to look left from your Nyquist diagram to find the -1 point, it means the corresponding pole is in the left half plane. If you need to look right to find the -1 point, then the corresponding pole is in the right half plane. Now, I'm not going to prove that. You can go to your maths books to see the proof, but that's the simplistic way of looking at it. So here's an example. We've got this system here, G equals 2s plus 20 over s plus 1 cubed. Are we stable or not? And you see I've got just G in blue and G over 10 in red. Well, if you look at the blue plot, here's the line of omega increasing. Which way do I need to look to see the -1 point? You can see the -1 point is there, and you can see I've got to look to the right. Okay, and because I need to look to the right to see the -1 point, then the corresponding closed loop is going to be unstable, and you could easily prove that on MATLAB. However, if I scale G by 1 over 10, you'll see now, in order to see the -1 point, I need to look to the left, and so now I will be closed loop stable. So the Nyquist diagram is giving you a very simple insight into am I closed loop stable or not, just by asking the question, do I need to look left? Do I need to look right? If you were to plot the root locus, what you'll see very clearly is it's stable for low gain, and then if gain is too large, the poles move into the right half plane, and you can see that matches this change from the red Nyquist to the blue Nyquist. Here's another example. Am I closed loop stable or not? So you can see here is the line of increasing frequency, and you can see to see the -1 point, I've got to look to the right. Okay, and because I have to look to the right, I'm going to be closed loop unstable. And again, if you look at the root loci, you can see here the poles are in the right half plane for all positive values of gain. And so the Nyquist diagram has given you this insight. What about this example? Am I closed loop stable or not, and how does that change with different gains? So here again you can see the positive frequencies, and I need to look left. You see, if I'm on that blue line, which is G, I need to look left, so I'm going to be closed loop stable if I just have G. What happens if I have G over 10, if I scale by 1/10? Now you can see I need to look to the right. So in this case, I'm closed loop unstable for low values of gain. And again, if you look at the root loci, you can see the root loci, right half plane poles for small values of gain, left half plane poles for large values of gain. So you're getting the same insight from the root loci and the Nyquist. Now, you can use the Nyquist stability criteria to establish a range of gains for which the system is closed-loop stable. So, for example, here you can see the intercept there is -1/8, and although it's not really showing the -1 points over there somewhere, so clearly the intercept can be shown to be -k/8. So if you scale by k, the intercept becomes k/8. You want to be looking left to be closed loop stable. So you basically need this intercept to be to the right of -1. So if k is less than 8, -1 is on the left of your intercept and you're closed loop stable. If k is greater than 8, -1 is on the right and you're closed loop unstable. Now here's a more challenging example. Here, again, if you look at the positive frequencies going around here, there's the positive frequencies. Where is the -1 point? And you can see you've got to look to the right. So for this particular example, if you had k equals 1, then you're going to be closed loop unstable because you're looking to the right to find the -1 point. However, the -1 point is seen by looking to the right. What happens if k is greater than 2? What happens now? Now you can see I've got to look to the left to see the -1 point, and I'm going to end up closed loop stable. So the Nyquist stability criteria. More formal derivations do exist which count in circumvents based on the entire Nyquist diagram and so on, and I'm not going to do that because for most examples it's sufficient to use the simple am I looking left or am I looking right, and if you want to be more rigorous, please go and look at the textbooks. Links to gain and phase margins. Just to finish off, with Bode diagrams we defined gain and phase margins as distance from stability, and the same definitions have an easily understood interpretation with Nyquist diagrams. So reminding you, the gain margin is the multiplicative scaling needed so the Nyquist diagram passes through -1, and the phase margin is the clockwise phase rotation so the Nyquist diagram passes through -1. So if you have a Nyquist diagram, these definitions actually make a lot of sense. So for example, here's the intercept. Here for this one it's -0.5. So what's scaling, if I multiply by k, will take that point to -1, and that's the gain margin. So here you can see the gain margin is going to be 2, because if I multiply by 2, that intercept gets to -1. What about the phase margin? Well, the phase margin is to do with rotation. So we find out where the gain is 1, and we ask ourselves, what angle theta, what rotation is needed so I can rotate this point to get to -1? And so that theta is the phase margin, that angle there. Okay? So some conclusions. We've introduced the Nyquist diagram for plotting frequency response information and shown that you can form rapid sketches of these diagrams using asymptotic information. And the insight gained from sketching is invaluable for design as it exposes the changes needed to ensure closed loop stability and good margins or performance. And if I do a little sketch here based upon that margin diagram that we've just seen, if you think about what we said before, oops, we want a phase margin of about 60 degrees. So you're basically saying, I need to keep my Nyquist diagram over here. I need to keep it well away from the -1 point. And then again, you can see by doing that, I'm looking to the left. Now in practice, what people tend to use is they tend to use Bode diagrams. So they say Nyquist has given us the insight into what's going on. Now that I've got the insight, it's actually far easier to do the design solely using the Bode diagrams, which is what we did in the previous video.